Good day, everyone. This is Chris back again with the Ancient Scholar. So today what I'm going to do is I'm going to talk more about the periodic table and the information it can give us. And I really should have probably done this as a first video, so I kind of apologize that this may seem kind of out of sequence. And really that first video was just kind of a beta test, and it just seemed to work out so well that I decided to post it onto YouTube without really thinking about starting at the more basic concepts. So I apologize if anybody's confused, but I still think that these are putting out some decent material, and hopefully some people find them helpful. So what I want to talk about is I want to talk about what we actually see when we look at an individual element. So if we say look at something like titanium here, and I'll go ahead and just mark that here. Titanium, what do all those little numbers inside of the box, the numbers and letters, what do they tell us? Well, if you see up here, I actually have a this picture rather has kind of a legend of all the information as to what you see on a typical or standard periodic table of elements. So the first thing, and let's go ahead and look at, well, this is boron here, so we'll just look at that, and that, of course, goes over there. So the first thing we see is this B in the middle. Let's do a different color here, something that... There we go. Okay, so we see this B in the middle here. That's known as the symbol, and every element has its own symbol. So hydrogen up here has an H, lithium an L, capital L, lowercase I, beryllium, capital B, lowercase e. Fluorine is just a capital F. Oxygen, capital O, nitrogen, capital N, neon, capital N, lowercase e, and so on and so forth. You can see all the elements. I know some chemistry and professors, instructors, teachers, etc. Like people to memorize a periodic table of elements. I think that's really kind of a waste. It's just a worthless exercise in rote memorization, and really I don't think is all that helpful. But what I think is more helpful is being able to look at the periodic table of elements and really decipher what it's telling us. I think that is more important and more fundamental to good understanding of chemistry than memorizing what a bunch of symbols mean. So that's just my personal bias. Okay, then generally on the periodic table of elements you'll have the element's name somewhere on there. We talked about inside, we'll stay inside of the box. We talked about the numbers outside of the box, so I'm not going to talk about those guys today. But if you see here on the upper hand left, now it can be in different places on different periodic tables. That little 5 there, and each element you see has it. Hydrogen, for example, is a 1, helium's a 2, lithium 3, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, neon 10, and so on and so forth, all the way down the periodic table of elements. Well, what that is that is the atomic number. The atomic number, of course, tells us the number of protons. So the atomic number is the number of protons in the nucleus. And that is, the way I look at it, is like a fingerprint. Is a fingerprint for an element. That tells us, in nature at least, how many electrons I can expect to find in just a normal atom in nature that hasn't undergone a chemical reaction or hasn't been ionized. So, for example, hydrogen has an atomic number of 1. That means it has 1 proton in the nucleus, and of course protons have a positive charge. So that means in nature I would expect that hydrogen to have 1 electron in a cloud somewhere around the nucleus. And of course I have a positive and negative. They're attracted to one another through something called the Coulombic interaction, or the electrostatic force, or the Coulombic force. Pretty much mean the same thing. And in nature, atoms are what we call neutral. That means basically the positive charge cancels out with a negative charge, and I don't have, the atom itself doesn't have an overall charge. So let's just go ahead and look at a few of these. Let's look at beryllium here. Well, beryllium has an atomic number 4. That's its fingerprint, so it has 4 protons. So we would expect in nature to have 4 electrons. So you can see how handy that atomic number is. It tells us a lot of information. Let's do one more. Let's go to the right here and look at arsenic. I'll circle arsenic here. Arsenic has an atomic number of 33. So we would expect to find 33 protons in the nucleus of arsenic and 33 electrons in a cloud around the nucleus. Okay, so that is the atomic number. Another thing that I have is I have another number that's usually typically it will be a decimal number. And what I'll do is let's just look at boron here, since it's kind of a little larger than everything. And you see this little number here, the 10.811. That is the atomic mass number. And basically what that number tells us is, on the average, an individual atom is going to have that much mass. And generally we only count protons and neutrons with the mass, because the electron, it does have a little bit of mass, but it's almost 2,000 times, has almost 2,000 times, or rather I should say a proton has 2,000 times more mass, almost 2,000 times more mass than the electron. So the mass of the electron is just really insignificant when compared to protons and neutrons. So if you see the 10.811, well, does that kind of seem interesting? Well, it should seem kind of interesting, because in nature, do we have half particles? That is to say, could I have one proton and a half of a neutron in the nucleus? Well, no. So we really shouldn't see decimals, but yet we do. What we need to realize is that decimal, that mass number, is an average. It is an average. And what causes that? Well, let's just go ahead and look at hydrogen here. And we can see the 1.0079 with hydrogen. So we know that hydrogen has 1 proton in its nucleus. And a proton has a mass of 1 AMU, atomic mass units. So what this is telling us is that if I take any hydrogen, it is going to have 1 proton and then this 0.0079 AMUs of mass. And I think a lot of people will go, oh, that's the mass of the electron. Actually, it's not the mass of the electron. What it is it says on the average, if I take all the different types of hydrogen, and what I mean by type is something called an isotope. Okay, an isotope is an element that has the same, it has to have the same atomic number. So let's just take hydrogen, for example. Hydrogen has 1 proton in its nucleus and 1 electron, and that's the normal 99.9% of all the hydrogen that we run across is this type of hydrogen. 1 proton, 1 electron. But what say that I have an isotope of hydrogen. An isotope is just something that has more or less neutrons. Well, we know that normal hydrogen only doesn't have any neutrons, but let's say that I now have hydrogen that has 1 proton, 1 neutron in the nucleus. So it would have a mass of 2 AMU, atomic mass units, much more massive than the normal hydrogen we find. But it's still hydrogen because it still has the proton. The proton is what tells us that it's hydrogen. Okay, that's known as an isotope of hydrogen, and we can also have a type of hydrogen with 1 proton and 2 neutrons. We call that tritium. If any of you guys are into shooting, you should be familiar with the kind of the glow-in-the-dark gun sights. Some of them use tritium, which is actually just a real heavy isotope of hydrogen that because the nucleus has so much stuff packed into it, neutrons and protons, it's unstable, and the nucleus decays. It breaks down, and when it breaks down, it gives off particles and subsequently causes light to come to us as it decays, releases that energy. So what this, going back to the point, what this number tells us here, this 1.0079, this number says that if I were to take basically all the hydrogen in the universe, and obviously this would be pretty hard to do, but on the average, if I were to take all the hydrogen atoms that ever existed, ever will exist, and I were to average them, the average mass for any one of those atoms would be 1.0079. That's what that's telling us. This also tells us something else, this atomic mass number, but I'm not really going to get into it in this video, but it is a way of converting the microscopic world of the atom into the macroscopic world through the agency of something known as Avogadro's number or the mole. I'm not going to talk about it now, but I'll just go ahead and leave you with that. Okay, guys, hopefully you found that intuitive, and as always, thanks for hanging in there.